Section 2.9, Dimension and Rank. So what is a dimension? We talk about dimension of a subspace, and later when we go into chapter 4, we will talk about dimensions of vector spaces. So here, dimension of a subspace H, which is denoted by DIM-H, it is the number of vectors in any basis for H. The dimension of the zero subspace, we define it to be 0. Because if we say dimension of a subspace is 1, then it means there is one vector which is kind of generating that space. So 0 only generates the 0 vector, only generates the 0, the origin. So its dimension is taken to be 0. Now what is rank? Rank is related to a matrix. So the rank of a matrix A, denoted by rank A, is the dimension of the column space of A. So it is the dimension of column space of A. It is not equal to A. So there is a rank theorem which says if A is a matrix and has n columns, so remember A could be an m by n matrix. So it has n columns, doesn't matter how many rows it has. Then rank of A plus dimension of null A will be equal to n. So this is a result that you have to kind of remember, and you could be asked question on this, where you have to use this result. The next is the theorem 15, which is the basis theorem. Remember, there can be more than one basis for a subspace. And here we see it says that let H be a p-dimensional subspace of Rn. Remember here p has to be less than or equal to n. P cannot be greater than n. So if we have a basis consisting of p vectors or p elements, then basically any linearly independent set of exactly p elements in H is automatically a basis for H. And in the next one, any set of p elements in H that spans H is automatically a basis of H. So here, note there are two different statements, like basically they mean the same, but here we know there are exactly p elements, and then in the basis, so in the set, then, and we know that H has a dimension of H is p, then that set will be a basis for the subspace H. But in the other case, let's say we don't know the dimension of H, but we know that we have a set of p elements of H which span H. So if that set spans H, then that is automatically a basis for H. So if you want to check whether a given set of vectors is a basis for H, you have to use one of these statements. Next, we talk about coordinate vector relative to a basis. So we usually, the vectors we have seen are related to the standard basis. So what is the standard basis? For R2, the standard basis, remember, standard basis for R2 is E1, comma E2, where E1 is the vector 1, 0, and the E2 is the vector 0, 1. In the same way, the standard basis for R3 is going to be E1, E2, E3, and now E1 will have, E1, E2, E3 will have three components. So the E1 for R3 will be 1, 0, 0, E2 will be 0, 1, 0, and E3 is 0, 0, 1. You have seen this before. But now we are going to see or learn how to get the vector from standard basis. How can we convert it to the given basis B? First, what is it called, or how is it denoted? Well, let's set B is equal to B1, B2 up to Bp is a basis for a subspace of H. Then for each x in H, the coordinates of the vector x relative to the basis B are the weights C1, C2 up to Cp, such that xb, so this is a new notation now, the vector x, and then we put b as an index. This is basically just the weights that we talked about earlier, C1, C2 up to Cp. But what are the weights, or how do we get them? They are basically the unknowns in this system of equations. So when you write x as a linear combination of the basis vectors, the coefficients of those or the unknowns here, these are the coordinates of the xb. How do we call it? We won't call it xb. It is basically called the coordinate vector of x relative to the basis b, or b coordinate vector of x. Okay, so, and we will do some examples, but before that we now want to connect the more things to the inverse matrix theorem, which we saw in section 2.3. There were we said that the statement A is an n by n matrix A is invertible if there were like 12 different statements. So combining the A is invertible. So A is invertible means the column space of A is equal to Rn. And then there were different things. The null space is 0. The transformation A to the transformation that takes x to Ax is 1-to-1, and bunch of others. You may go back and see that. But now we have more to add. So there were 12 of them. So the 13th now we say. So if the A is an n by n matrix, then the following statements are each equivalent to the statement that A is an invertible matrix. So the columns of A form a basis for Rn. So this is one statement. Another will be that the column A, which is a subspace of Rn, so this is going to be equal to Rn. So when the A is invertible, then column space will be equal to Rn, means column space will generate the Rn space. So if we are in R3, the columns, 3 columns, A should have 3, well, A should be a 3 by 3 matrix, and then those 3 columns, they generate the Rn3. And if we are in R4, then there should be 4 columns in A, and they generate the R4. Number 15 is that the rank of A will be equal to n, because remember, if all the columns are generating the Rn space, then the number of columns in A will be equal to n. In that case, the dimension of the null space will be equal to 0, because remember that rank theorem. So rank of A will be n, so the n plus dimension of null A will be equal to n, so which gives us null dimension of null A is equal to 0, which means basically that the null A is just a 0 vector. So these are some things we add to the inverse matrix theorem. Let's look at some examples here. So example 1, justify each answer or give a counter example. So here first is asking if the subspace of all solutions of Ax is equal to 0 has a basis consisting of 3 vectors. So if there are 3 vectors in a basis, what does that mean? It means the dimension of that space, subspace, dimension of H is equal to 3. Okay, that's what it means. Dimension of H is equal to 3. Now, here the first statement initially says if the subspace of all solutions of Ax is equal to 0. So what is that subspace? The name of that subspace is null A. So it means they are saying if null A has a dimension of 3. Okay. So this means dimension of null A is equal to 3. So let me write it over here. So dimension of null A is equal to 3. Then it tells us, and if A is a 5 by 7, so it means M is equal to 5 and N is equal to 7. So we have to find rank of A. So rank A is question mark. So what do? We go to our rank theorem, which says rank A plus dimension of null A. We don't need to put parentheses, but if you put them, it's not wrong. So dimension of null A is equal to n. So now just plug in what you have and get the answer. So we can say rank A, maybe I'll write it over here. Rank A is equal to, rank A plus 3 is equal to 7. So rank A will be equal to 7 minus 3 or is equal to 4. Okay, next one. If rank of a 7 by 6 matrix, so what does this give me? That M is 7, N is 6. So if the rank of 7 by 6 matrix is 4, which means rank is 4. So we have to find the dimension of the solution space of Ax is equal to 0. Remember again, what is solution space of A? That is the null A. So we have to find dimension of null A. So we use the rank theorem again. So rank A plus dimension of null A equals n. That is the theorem. Now I always write the formula every time I have to use it. That way I remember it, and remember that you are not allowed a cheat sheet or a formula sheet. So you have to remember these. So please write them every time you use them. So we have rank is 4. So plus dimension of null A is equal to 6. So that dimension of null A equal to 6 minus 4 equals 2. So the final answer is that dimension of null A is equal to 2. Next example, it says determine the dimension of the subspace H of R3 spanned by the vectors v1, v2, v3 given below. find a basis for H and find dimension of H. Now remember, we are talking about a subspace of R3. So it could be a plane, which means it could be a two-dimensional space, or it could be a line, one-dimensional space. So if it's a or it could be the R3 itself, which means in the basis there should be three vectors. So for a subset of the space, it can be a basis only if the vectors in the set are linearly independent and those vectors, linearly independent vectors, span the whole set, whole space. So we have to check whether these are linearly independent. That is the first thing I will check. And in order to check that, I'm going to solve, I need to do this, need to find, well, you can call them whatever, C1, C2, C3, or D1, D2, D3. Actually, such that A, D equals 0. Means all these D1, D2, D3 have to come out to be 0 in order for these three vectors to be linearly independent. So we solve the system, and so I have 2 minus 8 and 6. Then I have 3 minus 7 and -1. And then -1, 6, -7. These are our three vectors, and we are checking whether they are linearly independent or not. So basically, we could just go ahead with this 3 by 3 matrix. Just remember, these are the coefficients of our unknowns. But also you could do this, you could augment the 0 vector here, so that we can easily see that D1 is, are we getting D1 equal to 0, D2 equal to 0, and D3 equal to 0 or not. So we now reduce it, basically we try to get it to the echelon form. So it will be, since we have 8 and 6 in this, that we have to make 0, and we have 2 in the first row, first column pivot, so we will not get into fractions and divide the first row or multiply the first row by 1/2. Let's keep it as 2 and work with the rest. So we get that negative, 2 is positive, and then we have -8. So I can multiply the first row by 4 and add it to the second row. And then I can multiply the first row by -3 and add it to the third row. So what do I get? So the first row remains the same. The second row, it becomes 0 over here. Now 4 times 3 is 12. 12 minus 7 is 5. Then we have 4 into -1, which is -4. And then we have -7. Oh, sorry, and we have 6. -4 plus 6 is going to give me 2. Okay. What about the next one? I have to multiply by -3. So -3 into 2 is -6, and plus 6, so we get 0. Now 2 into 3 is negative 6. Okay, so we got that one. Now we have to multiply by 3. 3 into 2, it makes the first entry 0 here, then 3 into 2, 3 is 9, negative 9, and then negative 1. So I get negative 10. And then the last column of the coefficient, first multiply negative 1 by negative 3, which gives me 3 minus 7, negative 4. And this 0, 0, 0 just stays as it is. Now I will multiply the second row by 2 and add it in the third row to get this quantity 0, this entry to be 0. So I multiply the second row by 2, 2r2 plus r3. So this gives me 2, 3, negative 1, 0, 5, 2, 0, 0, 0. Okay, so what does that mean now? Now remember, we've had 3 coefficients, d1, d2, d3. So we didn't get a pivots in all rows. The third row has no pivot. It means d3 is the free variable, and which means the 3 vectors v1, v2, v3 are not linearly independent. So what else do we get to know from this putting our matrix into echelon form? We see that column 1 and column 2 are pivot columns. So which means the column 1 vector or the vector v1 and v2, these are linearly independent, not the vector v3. We have to kick vector v3 out. So the linearly independent vectors are v1 and v2. Therefore, the basis for H is P equals v1, v2. Now, why am I saying it that this is a basis? I didn't talk about span. Well, it was given to us that the H, the B basis, I mean, they gave us that the vectors v1, v2, v3, they span span our H. They span the subspace H. So what does that mean? It means v1 and v2 are linearly independent. v3 is on the plane which is generated by v1, v2. So v3 is included in this span. It's just like redundant vector. Basically, that is not helping the span with the span of v1, v2. So since the basis has a 2 number of vectors in the basis is 2, therefore dimension of H is 2. Okay, so this is how you can figure out what is the basis and how to look for the dimension of the subspace. I have two more examples. I will do them in the next video.